Okay, so in the last video we introduced generalized coordinates and figured out how to compute potential and kinetic energies using them, or to describe them. So now we're going to go ahead and actually derive Lagrange's equations of motion. So we'll start, and this will involve going through Hamilton's variational principle, which means I need to introduce the idea of a least action principle. Nature is full of these. Basically, a way that you can formulate many different fields of physics is to say that the actual path that some object takes seeks to make the value of some quantity or other an extremum, either a maximum or a minimum, it turns out, oddly enough. It'll turn out that in the case of mechanics, this quantity is a thing called the action. But we'll start with a more accessible example. We'll take a look at light. Now there is a thing due to Fermat's principle that says that the light time is an extremum. So let me just work through an example of that. So let's go and think about Snell's law. So say here's my interface between two media, index of refraction n1, index of refraction n2. This is my point A right here from which a light ray leaves. It is incident in at some angle theta 1, refracts out at theta 2 to arrive at some point B over here. Okay, so we can write the coordinates x1, y1, x2, y2, like so. Now, there are many conceivable paths the light could take. A really stupid one would be, say, maybe something like this, but we know that doesn't make sense. If the extremum is a minimum, which in this case it is, straight lines would clearly be the way to go. The only trick is to figure out where we hit the interface. So we'll go ahead and let this whole lateral distance here be x, between x1 and x2, like that. So the time of flight here in medium 1 would be equal root x1 squared plus y1 squared over the speed of light in that medium, which is the speed of light in a vacuum, over n1. And by the same token, same deal for t2, just replace all the 1s with 2s. All right. So then the total time of flight is t1 plus t2. So it'll be equal to n1 over c, just bringing that upstairs, times x1 over, times the, got ahead of myself there, times the square root of x1 squared plus y1 squared, plus n2 over c root x2 squared plus y2 squared. All right, now I want to find where this is an extremum at, and so the variable I'm going to want to play with is x1. So because x2 actually depends on x1, so let's rewrite it some more. n1 over c root x1 squared plus y1 squared plus n2 over c root x minus x1 squared plus y2 squared. All right. So to figure out where we're going to hit the interface, we will differentiate t with respect to x1 and set that equal to 0. All right. So differentiating this term is going to give me n1 over c, x1 over root x1 squared plus y1 squared. Then from this term, we'll get a minus once we take the derivative of what's inside. Be minus n2c x minus x1 over root x minus x1 squared plus y2 squared. And we can rewrite that as n1 over c x1, over root x1 squared plus y1 squared minus n2 over c. And now this is x2 and that's x2. So we're just putting that back in. x2 over root x2 squared plus y2 squared. Alrighty. But if we think about that, so we can rewrite this. You can multiply both sides through by c, and then rearrange a bit. So this becomes n1 x1 over root x1 squared plus y1 squared equals n2 x2 over root x2 squared plus y2 squared. And if I go and take a look at what x1 over root x1 plus y1 squared is, hey, that's the sine of theta 1. So I wind up getting n1 sine theta 1 equals n2 sine theta 2, Snell's law. All right, so that's the idea of how that goes. Now, what a clever dude by the name of Hamilton proposed was that a certain integral that we call the action, and it gets the symbol j, which is the integral from t1 to t2 of this quantity L dt, where L is a thing called the Lagrangian. So we'll get to that in just a second. Anyway, he proposed that this was the thing that we wanted to make an extremum. So it'll turn out that the Lagrangian has units of energy. So this is in units of joule seconds. So that's the units of action. So anyway, he proposed that this would be an extremum when evaluated along the actual path that an object took. So the way you formally write that is you write a lowercase Greek delta in front of your j, and that lowercase Greek delta is read as the variation in. So the variation in j, which is the variation in our action integral, t1 to t2, L dt, he proposed that that equals 0, and it turned out that was a good guess. Now this quantity L is called the Lagrangian, and it is equal to the kinetic minus the potential energy, not plus, minus. All right. So before we can go on any further with this, we're going to have to take one heck of a detour. And look at, and so we'll just be doing some math here. So we're going to have some fun with the calculus of variations. Now, I expect that you have not yet done anything with variational calculus. It would be a big surprise if you had. That's okay. I'll give you a crash course on everything we need. So we'll define some notation here. We'll let y prime be defined to be dy dx. So dots are still differentiating with respect to time, but this y prime will be dy dx. And so we'll just look at some integral, random integral I, that will turn into an action integral later. And we'll let it be equal to the integral x1 to x2 of just some function f of y, y prime, and x dx. So I can consider the trajectory that our particle might take. So we start here at x1, comma y1, end up here at x2, comma y2. Now the true and actual path that we take, let's say, is this. So this is our right path. We could think about some other path, say this guy right here. This would be a possible path that we looked at, but it was a wrong path. It was a wrong path. Now, the only thing that these paths are going to have in common is they have to start and stop at the same point. So what we'll do is we will characterize this right path as y of x comma 0, and then this wrong path was y of x comma alpha for some particular value of alpha. So we can write our path, our possible paths x alpha as being equal to the right path plus some parameter alpha times some function eta of x that gives us a recipe for how to deviate off of the right path. Okay. And this eta of x has a couple of constraints. We require that eta of x1 equal eta eta of x2 equals 0. Because all paths have to match at the endpoint, so regardless of the value of alpha, eta has to get us back home. All right. So then we can write our integral I as a function of alpha. So we integral x1 to x2. This will be some f of y of x alpha, y prime of x alpha, and x dx. Now, our extremum, because we want to minimize the variation in this, our extremum in this integral is going to be at this right path. So if I calculate di d alpha and evaluate it at alpha equals 0, that has to be 0. All right. So let's work on calculating di d alpha. So this will be, if I can bring the derivative inside the integral, that's okay. This will be integral x1 to x2. Now we're going to pick up some terms. We're going to have to do this as partial f, partial y, partial alpha, plus partial f, partial y prime, partial alpha dx. We'll call this integral star. All right. Now there are two terms that we will have to look at, so we'll just call them separately terms 1 and 2. So let's look at integral of term 2. That's going to be the integral x1 to x2 partial f partial y prime, partial alpha dx. All right, but remember what y prime was. Y prime was equal to partial y partial x, right, or dy dx. So that's going to become integral x1 x2 partial f partial y prime partial squared y partial x partial alpha dx. All right. Now, this we can integrate by parts. So this here, this partial f partial y prime is my u. Well, here, we'll just make it more obvious when we're integrating by parts. So I'll just rewrite first. So x1, x2, partial f partial y prime, that's going to be my u. And then partial squared y partial x partial alpha dx, that's going to be my dv. So then that's going to be uv, so it's partial f partial y prime partial y partial alpha evaluated x from x1 to x2 minus the integral. So we have the v times du dx part. So x1 to x2 d dx of partial f partial y prime partial y partial alpha dx. All right. Well, this first term here is 0. That's because all the curves have to pass through x1, y1 and x2, y2. And so the only way that can be the case is if partial y partial alpha vanishes at those points. All right. So now my integral star, from way back becomes partial I partial alpha is equal to integral x1 to x2 partial f partial y minus d dx of partial f partial y prime dy partial y partial alpha dx. All right, but this partial y partial alpha is just plain eta. Of x. All right. So I'm going to pull out of my backside a thing called the fundamental lemma. Of the calculus of variations. It says if integral x1 to x2 of some m of x eta of x dx equals 0 for all eta of x that is continuous through the second derivative. So I believe that's actually for all eta x smooth with 3 O's. Then m of x equals 0 for all x in the interval x1 to x2 inclusive. So that's just true. I'm not going to prove it. Somebody really smart did. So the only way, so what we get is that I is an extremum. if and only if partial f partial y minus d dx of partial f partial y prime is equal to 0. This is a big deal, and it has a name to it. This is called the Euler Lagrange equation. All right. So we could write some small variation off of our path as partial y. That would equal, variation of y, which would be equal to partial y partial alpha evaluated at alpha equals 0 times d alpha. And so similarly, our variation in our integral I would be equal to partial I partial alpha evaluated at the extremum d alpha. So our stationary or extremum path is the variation in I equals integral x1 x2 partial f partial y minus d dx of partial f partial y prime variation in y dx equals 0. All right, so that is the end of our math detour. So now we can go and apply that to our physics. So Hamilton's principle becomes variation in J, our action integral, is integral x1 to x2 partial L partial Q minus d dt of partial L partial Q dot times the variation in Q dx equals 0, where Q is our generalized coordinate. Now, if we have more than one generalized coordinate, our variation in the action that we demand be equal to 0 be equal integral x1 to x2 of the sum of these Euler Lagrange terms. So partial L partial Qi minus d dt of partial L partial Qi dot variation in the Qi dx equals 0. Now, since all the Qi are independent, each term in this sum has to vanish independently. So the only way that can happen is if the stuff in the square brackets is 0. And so we arrive finally at Lagrange's equations of motion. Partial L partial Qi minus d dt of partial L partial Qi dot equals 0 for I equal to our n, 1 to n generalized coordinates. This is known as the Lagrangian equations of motion. And this is true if all the forces are conservative. There are actually ways to extend this if you do have non-conservative forces, but it's usually a low margin approach. And our constraints are holonomic. Okay. So in the next video, we'll go ahead and do a bunch of applications of the Lagrangian equations of motion to see what they get us.